All right. Yeah, it looks like it's recording. Welcome everyone. Hello. I'm here to talk about spiking neural networks. Oh, we didn't unfreeze it. It's right here. There. Right.
Down is next.
You have to be select the page
There we go.
and then now.
All right. So ChatGPT takes a lot of energy to train, obviously. 190,000 kilowatt hours. So that's 1,000 watts per hour. And let's just say ChatGPT takes like it takes more than this, but like, let's say it just takes a day. That's already way more than it takes a brain to operate daily. All you're doing is eating food, right? You're eating apples, and that powers not just your brain, but running and all the other facilities of your body. But GPT is literally connected to an outlet that could cost way more energy. So the question is, what can we learn from the brain? The brain not does way more than ChatGPT. It does a lot more functions, way smarter. It's way more efficient. What can we learn from the brain to make our neural network models more efficient? So I want to pose a question to you guys. What can we do with low power artificial intelligence? How would that be useful? Save energy, yeah. Good for the environment. Yeah, I like that. I like that. What, you have something? No? Well, all this stuff too on the screen, drones, space. You can do little chips in your brain where you don't have access to an outlet all the time. You might want to print AI model on your chip that's already trained. So one key thing we have to understand here is what is a neuron? That's what our brains are made of. Okay, our brain is made of billions of neurons, and each neuron has 1,000 and 10,000 connections. So you can think about that. It's a huge number of connections. If you think of that analogous to neural network connections, even ChatGPT doesn't have that many connections. That doesn't have that many parameters as the brain. Obviously, they're getting there, but nowhere close enough. So the idea is that a cell, like, if you guys know what a cell is, right? A neuron is a way for cells, for these our cells, but they communicate with each other. They take in input at the dendrites, and if they get enough input, they send a signal down their axon to the terminal. And then that's where other neurons will be connected. I'll get more into that in a second. So there's this idea of the action potential. Yeah, neuron activation. Okay, we gotta learn how these neurons communicate. um, the cool thing about action potentials is that it's kind of like this electrochemical wave that gets sent down the neuron. And there's this rule we have to learn called the all or none law. And the idea is that once a membrane potential, that's like this voltage, it's the inner potential energy in the neuron, you can think of it like that. It goes up when it receives a signal, right? And once it reaches a threshold, it will always fire the same amount, the same amplitude, same wavelength. So the question is, if I am trying to communicate information with you guys, for example, I'm saying I have 4 apples, but I can't like raise numbers. I can't say 1, 2, 3, 4, right? I can only do 1, 1, 1, right? How can I do that? So the answer is that neurons communicate information over time, the 4th dimension, as we will like to say. The idea is that instead of saying 4, I have to do 1, 1, 1, 1, and then 4. Obviously, that's not exactly what's going on in the brain, but that's how information is encoded, it's how information is learned, and how information is represented. And obviously, if you don't reach the threshold, the membrane potential will go back down to resting potential. So like here are just some, that's from Fight Club. I don't know. All I'm showing you is that neurons are big, okay? It's just everywhere. It's in it's in our public ID. It's influential. It's literally how our brains work. Okay, that's what I'm telling you. Okay, that's all you need to know for that slide. So remember this throughout the presentation. Okay, that was a lot of information. Say neurons communicate with spikes over time. That's all you need to know. So, what do spiking neural networks learn from the brain? I posed this question before. So you gotta remember these 3 S's, okay? That's all you gotta remember. Spikes, it emulates spikes, sparsity, and static suppression. So the first one's obvious. Somehow, as I'm gonna explain later, spiking neural networks implement spikes in the neural units of the model. And then spikes lead to sparsity. So the idea is that if we are no longer storing floating potentials, we're communicating over ones and zeros, what does that remind you of? That reminds you of sparse tensors, sparse arrays. You don't actually have to store the entire array. You just have to store the time step where that spike is, right? You only have to store that index. That saves a lot of. And then the last idea is static suppression. So this comes more of like not from the brain, but more of our sensory perception and our retina, which is a part of your brain, if you're talking about photoreceptors. But the idea is that the brain responds not necessarily to every single frame like a camera. It responds to movement. It responds to changes. The brain, by trying to be economically and energetically efficient, if nothing's changing, it doesn't need a spike necessarily again because it's the same, right? So you don't, if you're looking at red, like if you're looking at flashing colors, right? If you show red, obviously the spiking rate will like be high initially for a red cone, but it'll go down because nothing's changed, right? You don't need to know that you don't need to like signal that it's still red because it's still red. So the idea is that if you use things like event cameras, these are special cameras that only react to change. This saves a lot of energy because it's not doing every frame. This information is represented in ones and zeros and spikes and times. You can actually use spiking neural networks to take advantage of this kind of event format or format of data. So does everyone here know how like perceptrons work or like the basic like linear layer? Does everyone know that? So the idea is instead of having these inputs that are floating point numbers, right? You have spikes, you just have ones that are implemented over time. And if enough spikes are happen in a certain time frame, a spike output would happen. Right? You see here, spike output 0, and then it will be 1. The spike happens. And then obviously the perceptron neural unit. Well, let's see. Yeah, so the perceptron neural unit is already based off of, I forgot what are the people that invented the perceptron? I forgot their name. Oh no, you'll learn that in your CSE 40 history. I forgot. But basically, it is based off a neuron, right? But we want to be more biologically realistic because we want to like draw more from the brain. Because already we know that the basic neural unit is so powerful. Like it's basically the basis of all the neural networks you have today. But we can also get really complicated with these Hodgkin-Huxley neural networks. Like, don't worry about like the fucking circuits. Okay, you just need to know like there's a balance between like too biologically realistic, where you're doing too many calculations to emulate the specific spikes of a neuron. And then there's also the artificial neuron, which is more general, but you aren't getting that kind of spike benefit with using a neuromorphic chip. So here's basically, I was showing you in the previous. In the middle, here's the leaky integrate and fire neuron. This is the neuron I'll be explaining today. And there's other types of spiking neurons, but this is one of the most simplest and easy to explain, and one of the like most used models because of its simplicity and its analogousness to the neuron itself. So don't be daunted by this equation, okay? I know it's massive, so hard, but okay, here, this is right here, Wx, does that look familiar? That's the perceptron, that's the linear layer equation, right? So that's the input. This is a weight, and you multiply that by the input. Now the idea is that just like that neuron graph we saw earlier, we need a way to decay and reset. And then we need a way to spike. Let me show you guys what I'm talking about. This graph, right? We need a way to decay right here. We need a way to spike if you reach a threshold. And yeah. So this is represented here. The equation where U is the membrane potential. It's that the energy in the neurons, the voltage. You can think of it all these kinds of different terms. And beta is the decay rate. So you can like that's just a hyperparameter. And basically determines how fast you decay, right? Smaller number, bigger decay. Because you're multiplying by a smaller number in the previous time set where t is the time. And then S is spiking, right? So here, if the membrane potential is higher than a threshold, right? Theta threshold, then you output 1. If not, it's 0, right? So you don't output anything. And 1 times theta is the 1 times theta is threshold. So you subtract by the threshold if you spike. So this is like one variant of reset, but I'll get into that later. Does everyone understand that? Any questions? So yeah, remember, there's the perceptron unit, the linear layer, decay, returning the resting rate, and resetting. It's that period of repolarization, hyperpolarization. I forgot to mention this earlier, but basically because this has to be the same wavelength, the same amplitude, this also has to happen. Sometimes called the refractory period, hyperpolarization. That means you can't just have like one output, right? It has to be spike, rest. There's like a maximum firing rate. There's also a minimum firing rate too, because if a neuron isn't firing, that means it's dead. So here's kind of like how we can visualize the membrane potential. If we have a constant input, right? Imagine you're just putting in like some kind of electric pulse into the neuron. You can just think of like all kinds of science experience when you do that. But here we can think of it as a constant input current. It takes some time, but eventually because of that weight and that decay, it will flatten out over time. But it's kind of like multiplying that over time, the decay. So it's kind of this curve. I don't know how to describe that, but a curved line. This is membrane potential, this is input. And here's this idea of a step where you turn it on, you turn it off. It grows. This is the integration. You can call the leaky integrate and fire. Integration is integrating the input into the membrane. Then decaying when there's no input anymore, it decays. So here is when you implement a threshold. And you can imagine when the potential goes up, if it reaches the threshold, you spike here. It's like a 1. And then you have to reset the membrane. And another key insight is that if you lower your threshold, right? So the threshold's 1, and the threshold is 0.5 here. This is the same input, but the number of spikes increase for the one with the lower threshold. And that makes sense because you reach the threshold faster, refit that faster, you hit the threshold. So I was mentioning, right? Neurons, they don't communicate in this constant input. We're not injecting like electricity into their brain, like that's not how the brain works. So when you have multiple linear layers, you have to have input spikes. And this is the same thing when you have that static suppression, when you're using event cameras, you also be inputting spikes. Integrate these spikes and do something, do more into a different kind of spike output. So how that looks. So I was mentioning the reset mechanism. In that equation, we talked about subtracting by the membrane potential. And of course, in actual neurons, it goes below the resting potential. And there's a one where you can reset by 0. But in like testing and just in the field, people have found that reset by subtraction, which is subtracting by that membrane potential, is better. We're not exactly sure why. Like, a lot of artificial intelligence hasn't been totally mapped out with the math, but that's just how it is. So that's the default on the library we'll be using later, but you can obviously change it because it's how the library works. So I'm gonna test your guys' knowledge. Hopefully you guys are paying attention, right? So what is this equation represent? What is S? Can someone answer that? The output? Yeah, but SP, let me get a hint. What word am I thinking of right here? Oh, there's spike. Got that? Okay. Now that we know this is a spike, like this is an equation about spikes, right? Determining if there's a spike or not. What is theta? Or what is actually let's talk what is U of T? Yeah, that's the membrane potential. Yeah, exactly. Threshold, yes, theta's threshold. We got this, we got this. All right. Okay, so that was the spiking equation, right? And the spiking, that's right here in this membrane potential. Talked about that, UT. Membrane potential equation. So remember, there were entries under here, right? So do you guys remember what they were? So decay, which one's decay? First one, decay, right? You're multiplying by beta, that's like 0 to 1. If that makes sense. Does anyone want to tell me what the second one is? Yeah. So like remember, that's the linear layer. Makes sense? And then, does anyone want to tell me that last one is? Reset. Ah, we did it. So you guys just learned a lot right there, right? So like, let's process that. But the idea is a spiking neural network will have those spiking neural units, and it'll comprise of the entire network, and the input will be spikes and the output will be spikes. So idea is, right, in classification, usually in a neural network, you just take what? Softmax, what's the highest number there is your classification, right? So how would you do that with spikes, right? One way you could do it is rate encoded. So the most spikes is your classification. That's what your prediction is. And then another way is latency. So it's just whichever spiked first, like whichever neuron has a first spike, that could be your classification. And the way your neural unit learns this is through like the loss function, right? So as long as you're training it in a certain way and interpreting the answers in that certain way, it'll learn to output it in a certain way, in that certain output. And what's interesting though is that while we see more like accuracy with the rate encoded one than the latency, it's impossible for like the brain for all neurons to be rate encoded because it's just too much energy for what we know the brain to be using. So that's still science we gotta figure out, So I was talking about spike encoding, and that was like on this previous slide here. Spikes in. Okay, it's not 100. You don't necessarily need to do spikes in, but it's better for taking advantage of that sparsity, right? You want sparse inputs takes less energy. So like this would be inputting this 7, right? MNIST, we all seen that. You could input 7 on every time step, or you could rate code 7 where white pixels fire more and darker pixels fire less. That makes sense, right? When you grayscale something, it's 0 to 1. You can interpret that as a probability. You can change that to an. So multiple ways. It's the same thing as before. You can do rate coding, brighter the pixel, more spikes, or brighter the pixel, the earlier the spike. Another way is if you have data that's delta modulation, some kind of frequency, you can make it so that spikes that at the peak of a wave, it'll spike, and at the trough of a wave, it'll do an off spike, or you can just do no. These are just ways to encode data spikes. So there's something we gotta address here, the dead neuron problem. So you remember that equation with the S before, right? So it spikes or it doesn't spike. Can we see how that might be a problem for backpropagation, where you have to take the gradient descent? Anyone have any ideas? Yeah. Exactly. So like if you take a derivative of a vertical line, that's infinity, right? And then if you take derivative of 0, it's 0, right? So the idea of backpropagation is you're trying to see what inputs had the most effect on that output. But if the output's just 0 or infinity, you can't tell like what is causing that neuron to fire, or what is causing that input, what effects, right? So this is a problem that we've been able to that there are multiple ways to like work around. I'll get to on the next slide, but yeah, great job. So addressing the dead neuron problem. One of the easiest, not easiest, but like one of the ways you can do it is you can take a pre-trained artificial neural network, convert that into a spiking neural network, where basically if the weights are higher, that just means more spikes, right? And then spike time gradient is this idea where, you know, if you're taking a gradient of this discrete function, right, where it's 0 or 1, it's going to get 0 infinity. But what happens if you took derivative in respect to time? That's not discrete. It's a floating number, right? It's like what time step we're on. Lastly, this is the most like used one, is surrogate gradient. So on the forward pass, we use that heavy side, that spiking function, right? We use it like normal. On the backward pass, we use something that's kind of close to it. We use something like an arctan, and it's called a surrogate gradient. Whatever you put in is called a surrogate gradient. So like as you can see before, right? It looks like this, right? Here, at certain threshold is 1, right? Below that threshold, 0. Instead, we will map on an arctan or something, and that will smooth it out, and then you can do gradient descent, then you can do the backprop. Before we move on to the code, does anyone have questions? So like, I'm not gonna like go into like the details. Honestly, I'm not specific. Like, I don't really do that much work in the time gradient stuff. But the idea is that, like, for example, we can see like what effect a certain spike has according to, well, the most fundamental thing to understand is that, for example, if you take this time, right, you can take the derivative of that because that's not like 0 or 1, right? It's like what, how many like what time step that is, that's a number. But I think the idea is that you can kind of see like when, according to the time something's like the membrane potential is. Like we're not tracking the spike, we're tracking the membrane potential. You can kind of see like what effects the membrane potential has on each other over time. Right? So like you're taking the loss with respect to F, which is the time gradient, and you take F with respect to U, the membrane potential. So yeah, come to this link and I will go to the link as well.